A single circular linked list is a powerful and flexible linear data structure that differs from a normal singly linked list by its unique circular arrangement of nodes, allowing continuous traversal without encountering a null terminator. In this structure, each node contains two parts: a data field that stores the actual value and a next pointer that refers to the next node in the sequence. However, unlike a normal singly linked list, the last node does not point to null but instead points back to the first node, referred to as the head of the list. This circular connection provides several advantages, such as the ability to traverse the list indefinitely, efficient memory handling, and convenience in applications requiring circular data flow, including CPU scheduling algorithms like round-robin, circular buffering, and real-time applications where processes repeat cyclically. The fundamental operations that govern and manipulate a single circular linked list include creation, insertion, searching, deletion, and display of nodes, each of which plays a vital role in maintaining the structure and functionality of the list. The creation of a single circular linked list begins with initializing the head pointer to null, symbolizing that the list is initially empty. When a new node is created using dynamic memory allocation, its data field is initialized with the required value, and its next pointer is set to point to itself. Since a new single node in a circular list is essentially a circular structure by itself, if the list is empty, this newly created node becomes the head. Otherwise, when multiple nodes are created sequentially, each node is linked by accessing the last node in the existing circular structure and updating its next pointer to point to the newly added node, while also ensuring the new node's next pointer is updated to point back to the head, maintaining the circular property. The circular nature ensures that there is no natural endpoint to signify the end of the list, making traversal continuous until explicitly stopped by the programmer using conditions. Insertion is one of the most crucial operations in a single circular linked list, and it can be performed in three primary ways: insertion at the beginning, insertion at the end, and insertion at a specific position in the list. Insertion at the beginning involves creating a new node, setting its next pointer to the current head, and then adjusting the last node's next pointer to point to this newly inserted node. Because in a circular linked list, the last node must always point to the head. Finally, the head pointer is updated to this new node, making it the starting point of the list. This ensures that the circular nature remains intact and that the new node becomes the first element. Insertion at the end is often simpler if a tail pointer is maintained, but even without it, one can traverse the list until reaching the last node, which is identified by the condition that its next pointer points to the head. A new node is created. Its next pointer is set to the head, and the last node's next pointer is updated to point to this new node, making it the last node of the list. This preserves the circular structure. Insertion at a specific position requires traversal from the head until reaching the node after which insertion is desired. A new node is created. Its next pointer is assigned to the next pointer of the current node, and the current node's next pointer is updated to point to the new node. This allows efficient insertion anywhere in the list without requiring shifting of elements, highlighting a major advantage over arrays. Care must be taken to maintain the circular link, especially if insertion is made adjacent to the head or tail. Searching in a single circular linked list is performed to locate a specific data value by traversing the list from the head node. Because the list is circular, a typical search must include a condition that stops traversal when the starting point, head, is reached again. ensuring that the loop does not become infinite. Searching begins at the head node, comparing each node's data value with the target. If a match is found, the corresponding node's location or pointer is returned. Otherwise, traversal continues. If the traversal returns to the head without finding the element, the search concludes that the target does not exist in the list. Searching in a circular linked list has a time complexity of O(n), which means that in the worst case, the algorithm must traverse the entire list before determining whether the desired element exists. Although this complexity is identical to that of searching in a normal singly linked list, the circular nature demands precise control of traversal to avoid infinite loops. Searching is essential not only for user-driven lookups but also for enabling other operations such as insertion at specific positions and deletion of specific nodes. Deletion in a single circular linked list is slightly more complex than deletion in a normal singly linked list because of the circular structure that must be preserved after deletion. Deletion may occur at the beginning, at the end, or at any intermediate position. Deletion at the beginning requires updating the head pointer to the second node in the list and ensuring that the last node's next pointer is updated to point to the new head. The memory allocated for the old head node is then freed. If the list contains only one node, deletion resets the head pointer back to null as the circular structure collapses. Deletion at the end requires traversing the list until reaching the node just before the last node. This node is identified when its next pointer points to the head, and its previous node is the second last. The second last node's next pointer is updated to point to the head, and the memory of the last node is delocated. Deletion at a specific position involves traversing the list until reaching the node immediately before the one to be deleted. Once found, the next pointer of this node is updated to skip the target node and point to the node after it. The memory allocated to the deleted node is released. Since circular lists do not have null pointers, careful tracking of traversal conditions is required to avoid infinite cycles. Additionally, special cases such as deleting the only node, deleting the head, and deleting the node before the tail must be handled precisely to preserve the circular structure. The display operation in a single circular linked list is used to print or visualize the list's contents. This operation begins from the head node and traverses each node until reaching the starting point. Again, unlike a normal singly linked list where traversal ends when the next pointer becomes null, traversal here ends when the pointer returns to the head. Displaying the list helps users and programmers understand the current structure, verify correctness, and debug insertions or deletions. It is essential to explicitly stop the loop when the head is re-encountered to prevent output repetition or infinite printing. The display method usually prints each node's data followed by an arrow symbol representing the link, such as data right pointing arrow, and ends by symbolically showing a connection back to the head, such as right pointing arrow head, emphasizing the circular property. In conclusion, the operations of creating, inserting, searching, deleting, and displaying nodes in a single circular linked list highlight its structural uniqueness, efficiency, and widespread applicability in real-world scenarios. Due to its circular design, it eliminates the need for null checking at the end of the list, supports seamless repeated traversals, and provides elegant solutions to problems requiring cyclic processing. Its dynamic memory allocation supports flexible growth, while insertion and deletion operations are more efficient compared to static structures like arrays. These advantages make the single circular linked list a vital data structure in computer science. particularly in operating systems, scheduling algorithms, buffer management, simulations, and many other fields where continuous looping behavior is essential.